Okay, let's dive right into this. Welcome to this explainer. Today, we are taking on a rather unusual job. We're stepping into the shoes of a night manager who is facing down an absolutely impossible, mind-bending puzzle. We're going to explore one of the most fascinating and frankly weirdest corners of mathematics. We're talking about a hotel with infinitely many rooms. A hotel that is completely 100% full, yet can still somehow fit more guests. So picture this in your head. You're standing in the lobby of a truly grand establishment. It has an infinite number of rooms, numbered 1, 2, 3, 4, and so on, literally forever. You look down at your ledger, and every single room is currently occupied by a sleeping guest. The hotel is packed, no vacancies whatsoever. And yet, if someone were to walk through those front doors right this second, you can absolutely guarantee them a room.
I really want you to think about that for a second. How on earth is this mathematically possible? If every single room is full, how can you possibly fit more people inside without kicking anybody out? Well, grab your night manager's hat because I'm challenging you to actively solve this paradox alongside us today.
To really get a handle on our new workplace, we actually have to rewind all the way back to 1924. This whole mind-bending scenario was first introduced in a lecture by David Hilbert. He was one of the most influential mathematicians of the 20th century, and he basically wanted to show just how counterintuitive an actual infinity really is. He called this thought experiment the Grand Hilbert Hotel, or sometimes just the Paradise. And well, tonight, we're the ones running it.
Okay, so the bell rings. It's late, and a single, very tired traveler walks into your lobby. They desperately need a room. But remember the catch. An infinite number of guests are already sleeping in your infinite number of rooms. Welcome to Boss Level 1. So what's your move? How do you accommodate this single new guest without throwing anyone else out into the cold?
Actually, what's beautifully simple about the solution here is the math. You just get on the loudspeaker and you ask every current guest to pack up and move over exactly one room. The guest in room 1 moves to room 2. Room 2 goes to room 3. Basically, you're asking everyone in room n to move to room n plus 1. And because infinity has no end, like there is literally no last room, every single existing guest easily finds a new spot. Suddenly, room number 1 is completely empty and your tired new guest can happily check in. It's like magic, right? Infinity just flawlessly accommodated a finite addition.
But of course, the night is just getting started. You look out the window and you see a bus pulling up. Except this isn't any normal vehicle. It's an infinitely long bus, and it is packed with a countably infinite number of passengers. Every single one of them is marching up to your front desk, and they all want their own room. Your hotel is completely full again. So what do you do now? You might panic for a second, but don't worry. Math has your back. You jump back on that loudspeaker. But this time, you ask every current guest to move to the room number that is exactly double their current room number. So, the guest in room 1 moves to 2, the guest in room 2 moves to 4, room 3 to 6, and so on. You're moving everyone from room n to room 2n. By doing this, you've just packed everyone into the even-numbered rooms. But look what you just freed up. Every single odd-numbered room, 1, 3, 5, 7, all the way to infinity, is now entirely vacant. You just hand the keys for those infinite odd-numbered rooms to the infinite line of people getting off the bus. Boom, solved.
Okay, so just when you think you've nailed it and can finally go grab a coffee, the situation escalates. You look out the window again, and it's not just one infinite bus anymore. It's an infinitely long traffic jam of infinitely long buses. It's an entire infinite fleet, and every single one is packed with an infinite number of passengers. The hotel is completely full. And if you turn them away, the hotel loses an infinite amount of money, and you're definitely getting fired. How on earth do you fit them all in?
Prime numbers are about to save your job. Around 300 BCE, Euclid proved that there are an infinite number of prime numbers. Numbers divisible only by 1 in themselves, like 2, 3, 5, 7, 11. So here's the trick. You take your current guests and you assign them to the first prime number, 2, raised to the power of their current room number. The person in room 4 goes to 2 to the power of 4, which is room 16. Simple enough? Then for the first infinite bus, you use the next prime number, 3. You assign them to room 3 raised to the power of their seat number. The next bus gets powers of 5, the next gets powers of 7. And because of the fundamental theorem of arithmetic, these numbers will absolutely never overlap. Every single person gets a completely unique room number.
Wow, okay. We've survived an infinite number of infinite buses. We've got to be invincible by now, right? Well, enter the ultimate boss level. A new massive party bus pulls up, but this one has no seats. Instead, the passengers are identified by name tags featuring infinite sequences of just the letters A and B. One person is literally named AAAAA forever. Another is AB forever. This bus contains every single possible infinite sequence of those two letters. And yep, you guessed it, they want rooms.
You try all your previous tricks. You assign room 1 to a guest, room 2 to another. You make this massive, infinite spreadsheet pairing every room to a passenger. But this time, it fails. The mathematician George Cantor actually showed us why. Take your infinite list of assigned guests. Look at the first letter of the first name and flip it. If it's an A, make it a B. Then take the second letter of the second name and flip it. Take the third letter of the third, flip it. If you keep doing this diagonally down your list, you instantly create a brand new sequence of letters. And because you deliberately flipped at least one letter compared to every single name on your sheet, this new name is absolutely guaranteed to not be on your list. No matter how clever you are with assigning rooms, this diagonal trick proves there is always going to be a guest left out in the cold.
So we did it. We finally broke the hotel. But why? Well, it turns out there are actually different sizes of infinity. I know, it sounds crazy. The number of rooms in Hilbert's hotel is what mathematicians call countably infinite, kind of like the integers 1, 2, 3, and so on. But the passengers on that last bizarre bus? They represent an uncountable infinity, much like the set of all real numbers, including the irrationals and infinite decimals. You just can't pair them up one-to-one with countable whole numbers. Our hotel was massive, sure, but it simply wasn't big enough for an uncountable infinity.
Now, you might be sitting there thinking, okay, this is just some abstract, purely theoretical math puzzle. Who actually cares? But the implications go way, way beyond pure math. Since 1924, this exact thought experiment has echoed through some of the biggest scientific debates of the last century. It shifted from numbers on a chalkboard right into cosmology, philosophy, and even real-world history.
Case in point, in 1947, the renowned physicist George Gamow used the Hilbert Hotel Paradox to explain the sheer vastness of the cosmos. He was heavily studying the expansion of the universe, and he used this exact mathematical logic to show that an infinite space could expand, or contract, without ever running out of room or contradicting itself. Suddenly, the hotel wasn't just a quirky building anymore. It was literally the blueprint for our infinite physical universe.
But wait, it doesn't even stop at theoretical cosmology. Fast forward to modern times, and we find something truly wondrous. This purely abstract mathematical concept is actually manifesting right in front of our eyes in classical modern optical physics.
Over in modern optics, researchers use these highly specialized devices called fractional spiral phase plates to manipulate light waves. And astonishingly, in 2015, optical physicists realized that the way light behaves when passing through these specific plates is a nearly perfect, literal realization of Hilbert's hotel.
It's wild. When a light beam passes through the plate, it creates these things known as optical vortices, which have a specific topological charge. Now, because that charge has to be conserved, you can't just spawn one out of nowhere. So what does the light do? It creates an infinite chain of vortex pairs. Think of the positive charges as our hotel rooms and the negative charges as our guests. To free up a charge, a guest essentially steps out of their room and moves to the room next door, all the way down an infinite chain, leaving exactly one unoccupied room behind. The light waves are literally executing our exact night manager's trick.
So what's the big takeaway from surviving our shift as the night manager at Hilbert's Hotel? First, infinities are absolutely not all the same. There are quite literally different sizes of forever. Second, the math behind this paradox deeply shapes our understanding of a potentially infinite, ever-expanding cosmos. And finally, these wild abstract theories aren't just in our heads, they actually manifest in the physical world, dictating the behavior of real light waves in a laboratory.
We've seen that the math works, and the light waves prove it's a physical reality on a small scale. But what happens when we look up? If the universe is indeed infinite, which kind of infinity is it? Is our physical reality a countable infinity, where we can always find a little more space just by shuffling the cosmic furniture around? Or is it an uncountable infinity, far larger and more terrifying than our human minds can even begin to map out? It's definitely something to chew on the next time you look up at the night sky. Thanks so much for joining me on this explainer, and I'll catch you next time.